All right, grade 12s. Today we are going to move on to, we're going to split this next one into two parts. We're going to be talking about the motion of charges inside of electric fields. So just to remind you about our last lesson that we talked about, the last thing that we discussed was how inside of parallel plates, we can connect all of these different formulas to one another to help us to be able to solve them. So more than ever in this class, it's important to just write down all the information you've been given in a certain problem, because then you just come back, you reference this kind of master formula, and you just pick out the parts that you have and what you need and decide what route is going to work best to solving that based on this formula. So we're going to continue on with that idea. And what today, when we're talking about motion, we know that we're talking about kinetic energy, right? So today we're going to relate all of these formulas to kinetic energy, which, just a reminder, is 1/2 mv squared, right? So that's going to be the focus for today. Now, before we do specifically that, we are going to look at what kind of behavior the electric field has between two parallel plates. So if I have a scenario like this one, and I've got a series of parallel plates here. Now, this little battery right here on the left is just showing us where our voltage is coming from and where that electric field is being generated from. So you don't actually need to draw that. Normally, you'll see the drawings like one below, but just a little technicality there. So what this is telling us is that if I go from the top plate to the bottom plate, or from the bottom plate to the top plate, I would go through a potential difference of 100 volts. Okay, so that's what that battery right there is telling us. Now, what the question is saying, though, is what potential difference would that charge that I move go through if it was only moved 5 centimeters instead of being moved the full 10? So say, for example, I had a charge up here at the top and I wanted to move it down here. Now, we're not concerned with what its actual charge is. We're just looking at the distance I move it. So now, instead of moving it 10 centimeters, I only moved it 5 centimeters. What would happen? The answer ends up actually being really straightforward, probably exactly what you would imagine. When I look at this, I look at 10 centimeters, and that's a potential difference of 100 volts. Well, in this case, we look at 5 centimeters. I think our first guess would probably be that it would be 50 volts. That is right. I'm going to show you why. So in this case, we have something called a uniform electric field. Okay, I'm just going to call it shorthand uniform E, because we know now that E stands for electric field. Okay, what this is telling us is that the electric field at any point throughout these two plates is the same. So it's the same, I've got my mouse in the way here. It's the same at all points. Okay, now what that tells us then is that it doesn't matter where we're at, our electric field at, say, 10 centimeters, right? If we traverse the entire parallel plate system, is going to be equal to the electric field that we have if we only travel 5 centimeters, if we only move it 5 centimeters. So what I have there are my little subscripts giving me my distance value. So my electric field at 10 is equal to my electric field at 5. What that ends up meaning, if I go back and look at, I think it was one of the first formulas that we learned in this section, is that the electric field is equal to the potential difference divided by the displacement. That's actually not right here, but it's a rearrangement. It's a canceling of the charges here, and then we just divide by displacement. So we get potential difference divided by displacement. Now we know that for E10, we know what that's going to be. Right, that's going to be potential difference at 10 centimeters divided by a displacement of 10 centimeters. But that's actually going to be, it's the same thing kind of like with always with our conservation of energy or conservation of momentum. Because we have uniform electric field, we can set it equal to what it is here too. So it's going to be equal to what it is through a potential difference of 5 and a displacement of 5. Now, I know what delta V10 is, right? Let's write that down. Delta V10 is 100 volts. I know what delta D10 is. It's 10 centimeters. Let's convert that to meters just to be consistent. So delta D10 If I have 10 centimeters, that's 0.1 meters. And then my delta D5, so 5 centimeters, is 0.05 meters if I do that conversion, right? And what we're trying to find is what is delta V5? What is the potential difference at 5 centimeters? So let's take these values and plug in what we know. So 100 divided by 0.1 equals delta V5 divided by 0.05. And when we solve for that, we end up getting that delta V5, the potential difference at 5 centimeters, like we had guessed, is just going to be 50 volts. So just showing you where that comes from. It makes our lives a lot easier, knowing that the electric field is constant or uniform throughout the entire distance between the two parallel plates. So our next step here is now we take this idea, and this helps us knowing this. We're going to use it again for the next problem. But now what I want to do is I want to relate it to what it looks like for the motion of the charge between those two plates. So when a charge is placed in an electric field, it may begin to accelerate to one of the charged plates. I mean, most likely it will, right? Because our charge is going to have a positive or a negative value. And then if it's positive, right, it's going to want to shoot away from the positive plate and towards the negative one. And if it's negative, it's going to want to do the opposite. We can find what the speed of that charge is using our kinetic energy formula, okay? Or we don't always use kinetic energy. We can actually use the dynamics or the kinematics equations as well. Because once we find those key values that we need, like final velocity, right? Because we're going to be using kinetic energy, so we'll have 1/2 mv squared. Once we find that final velocity, we know how far it's traveled. If we know how long it was traveling for, well, then obviously we know we can find its acceleration as well. This is going to end up relating back to these dynamics and kinematics equations that we started with when we're talking about the motion of the charge. So let's take a look at this example. An electron has a mass of 9.11 times 10 to the negative 31 kilograms and has a velocity of 2.5 times 10 to the 4 meters per second when it enters into the top plate. So when it enters in the top of the parallel plates. Now we know that those parallel plates have a potential difference of 300 volts and there's 6 centimeters of separation. So what our question is asking us is what is the velocity of the electron after it's moved 2 centimeters? So just like above, it's got a uniform electric field, which what that means is that our electric field for the total 6 centimeters, so E6, is equal to the electric field for the 2 centimeters, right? Just like we saw in the last question. So E6 is equal to E2. That's like the first thing that pops out at me when I'm seeing that. So we're trying to find what V2 is. Now this is where it's a little bit confusing because V2 obviously means its final velocity. We can't get that mixed up with our potential difference, which is an uppercase V, right? Delta V, 300. I think in this scenario, more than any other question that we've really seen before, it's really, really, really important to write down all the information that we've been given in the question, because then, like I said, we go back and we reference that little master formula that has all the problems or all the variables in it, and we just pick which one makes the most sense for our question. But before I start anything else over here, I'm just going to write down here, I'm going to make a list of all the information that the question is, okay? Even the ones that are kind of you know, hidden within it. It tells us that we've got an electron. We kind of need to recognize that when it tells us that it's an electron or a proton, that is actually a way of telling us what its charge is. All electrons, a single electron, will have the same charge, 1.6 times 10 to the negative 19 coulombs. Now it told us the mass, that's the mass of an electron, is 9.11 times 10 to the negative 31 kilograms. Let's just keep going through here. The displacement that it goes through, well, it says what's the velocity of the electron after it's moved 2 centimeters. So our delta D is equal to 0.02 meters. Our final, our initial velocity, it tells us, right, V1 is 2.5 times 10 to the 4 meters per second, and we are trying to find V2. Okay. Now let's take a look. So that's all the information we have right here so far. But what I'm seeing here is that I have mass, I have displacement, I have charge, and I have velocities. And when I look at this up here at from the last lesson, it's not looking like I have exactly what I need. I have mass and velocity, which is nice for my kinetic energy, but I only have charge and displacement. I don't have electric field yet. But what I do have is I have this formula right here. I have basically the exact same setup that I went through from the last one here. I know what the potential difference for the total thing is. So maybe let's write that down. Potential difference for the 6 centimeters, 6, is 300 volts. But now I need to relate that to, I need to find what the potential difference for 2 is. Once I do that, then I can move on. So let's do basically the exact same thing that we did in this last question here, right here with E6 and E2. So that means that I have delta V6 over delta D6 is equal to delta V2 over delta D2. And what that ends up giving us is delta V2 is equal to delta D2, which we said was, I'll put this 2 here, is 0.02 centimeters, times delta V6, which we've written down as 300 volts, and then over delta D6, which we just know that's delta D6, is equal to 0.06 meters. So that goes here, 0.06. So delta V2 is equal to 100 volts. If we plug that into our calculator, that's we get 100 volts. Okay, so that's really important. That helps us a lot because what that ends up giving us now is this last little key piece of information that we need down here. We just found it. It's 100 volts. So now what we do is our next step here is to go to our little master formula thing, I keep calling it here, and pick out the parts that make the most sense. We know charge, we want to know velocity, so we know that we need to use kinetic energy, but we know charge and we now know potential difference for the 2 centimeters. So we have Q delta V is equal to the change in the kinetic energy. So that's what we're going to use. Q delta V is equal to the change in the kinetic energy. Now, just to be a little bit even more straightforward, change in kinetic energy is 1/2 mv2 squared minus 1/2 mv1 squared, or F's and I's, right? Initial and final. Just put a little dotted line here so we don't get confused. Okay, so we're almost there. Now all we need to do is we need to solve for V2, right? So if I solve for V2, first off, what I'm going to need to do is I'm going to need to add my 1/2 mv1, that's supposed to be a 1, squared on both sides. 1/2 mv1 on both sides. And then I'll multiply by 2 to cancel out my 1/2. And I'll divide by m, and then I'll take the square root, right? So I can kind of actually have all that happening here. It's times 2, and then we're dividing by m, and then we have v squared equals that whole thing. So let's write it all out. V2, and let's go squared. Let's keep it as squared, is equal to Q, let's do it this way, Q delta V plus 1/2 mv1 squared divided by, I'm just going to keep this as a whole kind of chunk together. Maybe that is a little bit more straightforward. Divided by 1/2 m. Okay, so even what I did here, let's forget about that. I think this way is a little bit more straightforward. So I just divided by 1/2 m because it was like it was multiplied by v2. And then what we end up doing is taking the square root of both sides. Okay, so V2 is equal to the square root of, we're going to have to try to, keep our writing relatively small here. We might run out of room. 1.6 times 10 to the negative 19. That's our charge. Our potential difference is 100 because it's for 2. It's V2. So 100, it's at the 2 centimeter mark, plus 1/2 the mass, which is 9.11 times 10 to the negative 31, times V1, which was 2.5 times 10 to the 4. I'm running out of room here. Squared over 1/2 times, do this, just keep using brackets, 9.11 times 10 to the negative 31. And all of that under the square root. So kind of a crazy, turns into kind of a crazy question, honestly. Some lots of actually really small numbers being used, but lots of digits going on there. What you do if you get that, you should get something like 5 point, take a look, 5 point, well, it's technically 1 sig fig. So I'm gonna say 5.93 times 10. I don't like that, just because it's going to change the numbers so drastically. Times 10 to the 6 meters per second. And you know what? Let's make this a vector. We know that it's going down. Okay, so there's our, and then we'll just go 1 SF because I don't want to change the number that much. So there's our final answer. Let's go with this color. That's how fast that electron is going to be moving after 2 centimeters between those parallel plates. And it's an electron, so it's negative. So it makes sense that it would be accelerating downwards towards that positive plate, right? Because the opposites attract. So there you go. That is it for today. We will do the second half of this lesson tomorrow, where we will get into just another example. It's a 3-part example. It would take me another little while. So I don't want to make this lesson too long. So we'll call it there. You can start to take a look at some of those practice problems if you want, or you could just do this and then you can work on them tomorrow after our lesson as well. And you'll have Wednesday to work on them as well. We're making good progress though, so make sure you're keeping it up and let me know if you have any questions. I will talk to you tomorrow.